Welcome back, and today we're doing some calculus in Python. This is a problem that I just got from one of my students, and I thought it would be interesting to take a look at how we can use Python to approximate the roots of a cubic equation. And in this case, we know it will be an approximation because this could have irrational roots, and therefore we couldn't rule out that the Python would not be able to give us a precise answer. The idea for solving this would be to use the Intermediate Value Theorem, and what that says basically is if we have a value for the function where it's less than 0 and we have a value for the function where it's greater than 0 and it's continuous between those 2 points, then somewhere between the 2 points we should have a root. And so the way we will use that in Python is we will search midpoints recursively using the Intermediate Value Theorem until we have an approximation for the root that is within some small neighborhood of 0. Okay, the first thing we want to do is set up our function. So to do that, we are going to say, we're going to call the function f, and we can do this as a lambda, and the parameter will be x, and the expression is this one up here. Okay. And my code editor turns that into a function description instead of leaving it as a lambda, but you're welcome to do it either way. The next thing we need to do is think about how to find values of this function that have opposite sign. And you could get nuanced on this. We're going to do a little brute force because we have Python to do a lot of the heavy lifting. So what we're going to start out with is we always know one of the values could be 0. Right? So let's do find starting x. Okay, x's. And this is going to take in a function, and what we would like to do here is abbreviate this to function fnc so that we can call it up easily without having to type too much. And we're going to set our initial point to 0, and then we'll say if, so it's possible that our function will actually be equal to 0 right there, will return true, and then we can basically just test whether this is pointless, right? And then otherwise we want to basically set an x2, which would be the other coordinate, and this is going to be equal to, we'll just start it out, equal to x1. And then we want a second point because we are going to have to increment both to the left and to the right of 0. So I'm going to set this out with x2b. And then what we'll do here is we want to set a step, and to determine how much we want to step in our search, I think what we could do is just take the difference between 2 points in this function. So what we could do is just say the step will be the difference between f of 1 and f of 0, and we're going to step by that much. And actually in this case the difference between consecutive integers will actually increase quite rapidly because of that cubic. But we're just going to stick with that. And so that's our step. Now we need to also be able to step into let's assume that's positive. So that will step us to the right of 0. We also need to step to the left, or vice versa. So we need a second step, which is just going to be step 1 times -1. This will step us the opposite direction. So in the search for x2b, we'll use step 2. In the search for x2, we'll use step 1. And then we want to just run through these steps. So basically, while function value at x2 times the function value at x1 is greater than 0, which means that they have the same sign. And the function value at x2b times the function value at x1 is greater than 0. Keep going. So x2 plus equals step, and x2b plus equals step 2. And we keep doing that until we break out of the while loop, which means we've found a good candidate. And basically, if it's x2, then what we'll find is that now this is going to be the f of x2 times the f of x1 will be less than or equal to 0. And then we want to return x1 comma x2. Otherwise, it's going to be the other one, and so we'll return x1 comma x2b. So this will search by step through these numbers, and then we'll find values for these. Next. Let's just see if that works. So we want to print out find starting x's on our function f. We'll run that, and there you can see it gives us a 0, negative 3020. And that's great. So negative 3020. And so you can see that's basically tells us that it ended up using x2b because it's negative in this case, which is great. So that means it works presumably in both directions, whichever way we need to go. Now, the next thing we need to do is figure out how we are going to search through the intermediate values, and we want to do this recursively. So we want to define a function, I'll just call it solver, and this function has to take a first parameter, a second parameter, and a neighborhood, NBHD. And basically we want to evaluate the function at the midpoint of these two values, and if it's within the neighborhood, then it's the solution. Otherwise, we are going to move. So first of all, we want to get the midpoint. That will be equal to the average of the two, x1 plus x2 divided by 2. The next thing we want to do is just check in case if, and this also can take a function in the solver. Okay, so if the function at the midpoint is equal to 0, we will return so not necessarily only equal to 0. So if it's in the neighborhood, that's enough. So if it's less than NBHD and FNC at mid is greater than -1 times NBHD, then we return mid. We return the function value at mid. Nope, it's going to be mid. No, right? The x-coordinate for that value. Okay, now once we're past that, we know that mid isn't close enough. So basically what we want to do is determine which direction do we continue. So if mid has the same sign as x1, so if FNC on mid times the function on x1 is greater than 0, then they have the same sign. So we need to run solver again, this time on, so x1 and mid have the same sign, so mid will replace x1. x2, the same neighborhood applies, and the same function applies. Otherwise, we know it's just going to go the other way, and we're going to run the solver by replacing x2 with mid, and then run the same neighborhood and the same f and c. Okay, now we can actually give this a go. So rather than calling up x1 and x2, how do we want to do this? Yeah, so let's call up x1 and x2. So x1, x2 will be equal to find starting x's on the function, and then we call solution will be equal to solver on x1, x2, 0.001 as our neighborhood. It's kind of accurate. And then for our function f. Okay, so the solution, and then we'll just print out the solution. Okay, and then we don't need to print this anymore. So it's just printing our x coordinates. Okay, let's run this, see what kind of errors we generate. None. And you can see it's printing out an answer. -8.4766, so on and so forth. Let's go really inaccurate here. You can see that even if our neighborhood is relatively small, we still get a pretty close approximation. But let's see if we can go a little bit bigger on our neighborhood. Let's say if our neighborhood is like 0.9, still gets a pretty good accurate solution. Let's say if our neighborhood is 10, still gets a nice solution, right? It's very interesting. I'm actually kind of intrigued why our neighborhood can be so far off. So basically this is just waiting for mid to fall within the neighborhood. Let's say 200, 2,000, 3,000, or 30,000. 50,000. There we go. So now we've got some inaccuracy, right? So this is a really tolerant bit of business here, which is quite intriguing to me, that we are able to do this. But it's great. Let's change this. Let's change our function. See, this has such large values. I think that's what's leading to this tolerance. Let's just see what happens. I don't actually know what's going to happen. First of all, let's validate this. Okay, so let me validate this. Let's do a neighborhood of 0.000000001. And let's see, if this doesn't give us a recursion error, which it doesn't, this should give us a really close approximation. So let's bring up Wolfram alpha, which will give us the solution to this problem. So here you can see our input and our solution right here. So what we want is to have Wolfram give us as many digits as we can get. It's thinking about it. I might need to refresh. Let me refresh that. Here we go. More digits, please. There we are. And let's get even more digits. And then I'm going to pull that in to code and just paste it down here below. So you can see that the accurate to many, many decimal places is going to be very close to our solution. And you can see they differ here in the many millions of millions, thousands of millions, whatever that is. Very, very accurate value here. Okay, let's go ahead and give this a change. So get rid of that, and let's change our function. So let's make this just like 90, and this one will be 500, and this will be 65. Okay, so I'll grab that. I will take that over to Wolfram Alpha. I have no idea what the solutions are on these, so hopefully this will work out for us. And let's pick up this one, bring it back into code. And find out what our solver tells us. And our solver does a pretty great job. So that one is going to be accurate 6 to right here. Accurate to there. So again, reasonably well accurate. Let's just see if we can get an extra recursion depth out of that. We can. And does that bring in any more accuracy? Yeah, because now they agree on that 7, right? See if we can go a little deeper. And we can. Go again through our stack. We can. And again. And again. And again. We're not getting any new accuracy. No change in results. So let's pull that in. And that's as accurate, presumably, as we would get using this data type, because we're not really making any difference here as we go out. So that's really quite accurate. Okay. Yeah. So I hope you enjoyed that video. I hope you learned something. If you have any ideas for any other videos, just leave them in the comments. Thanks.